Okay, so we're going to look to integrate this function here from 0 to 2 pi, and the function we're going to integrate is cosine of x divided by 5 minus 4 times cosine of x dx. Now how are we going to integrate this? I mean, trig sub is not going to work with the two cosines. Integration by parts definitely going to work. We're going to have to kind of try and force some other method. So as we're going from 0 to 2 pi, there's a method we could use in complex analysis. So now we're going to transfer this over into a complex form. So what we do now is, so we take the integral, and over let's say an integral over the range of r. So if we let r, let's write it on here, so we let r a region be where z is the unit circle. So that will give us our 0 to 2 pi. So let's draw the unit circle on here so we can see. That's our unit circle with radius 1, and then we draw the complex coordinates on here, imaginary. This one is I, here's minus 1, here's minus I. So that'll be our region R. So that would take care of our parameters of integration. And now we just put these into t, into the t world. So now we go cosine of t, 5 minus 4 cosine t, and then dt. Okay, so now when we're going into the complex world, we need to translate these cosines into their complex form. So what we do say is now is that cosine of t, that is a half of z plus z to the minus 1. That's the complex form of cosine. So now we import those into there. But now as we're going into the z world, we need to change this dt to be a dz. And then what we do say is that dt then becomes 1 over I z dz. Okay, that's all the bits put together now to translate this into the z world. So now we rewrite the integral over the perimeter of r. So we see a cosine t, so we write this. So we got 1/2 z plus z to the minus 1. And then 5 minus 4 times this. 5 minus 4 times 1/2 z plus z to the minus 1. And then let's put dz here and the iz on the bottom. So that takes care of the 1 over iz dz. Okay, now what we're going to do now is try and simplify this up now and try and come up with some kind of thing we can take the residues of. So at the moment we can't take the residues of this at all. So let's multiply top and bottom by z to get rid of this z to the minus 1. So now we're going to multiply by z over z. So now we've got region R, that stays, z times a half. Well, the half we can bring out the front, so that's a constant multiple. And now we're just left with z plus z to the minus 1, multiplied by z. That gives us z squared plus 1. So that takes care of this. Now this one, we can multiply the 5 by z, that's not a problem. And then minus 4 times z, well, we've got 4 times a half here, so we could just do that all in one go. So minus 2 and z. So minus 2z, and then z plus z to the minus 1. Okay, and then we've still got the I and z and dz. So the dz goes here. The I can also come out front as well because that's a constant multiple. So the I in the denominator becomes minus I when it's in the numerator. So if we change this to a minus and make that into an I, so minus I over 2, and then we've still got this 1z here, which I'm now just going to put like that. Okay, so we still can't take the residues, but what we could do is maybe do something with this z here. Let's distribute this z and we'll get some sort of polynomial, because we get this z times z to minus 1 will just become 1. So let's trust our luck on that one. So let's start off a new line. So minus I over 2, and then multiplied by z squared plus 1 in the numerator. That's fine. Okay, let's distribute this z. So 5z squared, and then minus 2z squared times z plus 1. Let's call this now 1 over z. So that's probably going to help us a little bit now when we come to simplify. And then dz. So just write that up there. So this z is now taken care of. So the region is R. Let's make sure we put that in. Okay, right, let's simplify this up. So that takes us again to minus I over 2. Again, just a complex number, but it's a constant multiple. Z squared plus 1. Okay, 5z squared, that can stay. 2z squared times z becomes minus 2z cubed. Let's try and write the z and the 2 so they look different, so the 2 a little bit curly there. And then we got 2z squared times the plus of 1 over z, but with a minus sign here. So now we're going to have minus 2z. Okay. Right, let's take a z out of this, because at the moment now we're getting on the way to find the residues here. Z squared, z cubed and z. So if you can factor out the z, and then maybe factor out again. Okay, and don't forget the dz on here. Okay, now let's do something here with this minus I over 2. So if we've got 2z cubed as the highest part order of the polynomial, let's try and get rid of this 2 by dividing this whole thing by 2. So we've got 5 we can divide by 2, this will divide by 2, and ideally that will divide by 2. Then also the minus sign, let's distribute the minus sign in here so we get a positive. For this sign here, this become a negative, this become a positive. That's going to be easy for us to factor. So let's do that one step at a time. So minus I. Okay, this minus 2, that become the 4. So I've got minus I over 4. Integral over R, z squared plus 1. Now what we'll do is distribute this minus sign in here to flip all these signs. So that can now go, and we'll distribute the minus sign in here. So now we can write the 2z cubed first, because that's now positive. Minus 5z squared, but don't forget we're dividing everything by 2. So minus 5 over 2z squared. And then this one here will become plus 1. So plus 1z. So plus z. Okay, and then we're still dz. So we haven't integrated anything yet. We're still trying to find the singularities and the residues. So let's rewrite this out now. So we now get I over 4 over the region R, z squared plus 1. That stayed there all throughout. Right, now let's factor out the z. So we got z. Sorry, the 2 goes here. Take this 2 out, we've taken the 2 out there. Z, so that's z cubed, so that's z squared, minus 5 over 2z, and plus 1. Now we've got something we can factor out now much easier. So z minus 2 and z minus a half. So 2 times minus 2 times minus a half give us plus 1, and then add them together we get the minus 5 over 2. Then we're ready to take the residues. So let's cross this off here. Let's start our working out back up top here. Okay. So, right, let's factor this out again. So I over 4 integral over r z squared plus 1. Okay, so let's keep the z. And now z squared minus 5 over 2z plus 1 will become z minus 2 z minus a half dz. So multiply that out, we get back to this. So we haven't changed anything. And I mustn't forget my dz here. Okay, so now we can work out the residue theorem. So if we take the residues of this function, so if we let f of z equal z squared plus 1 divided by z, z minus 2, z minus a half, and then if we take the residues of this function, then that's going to give us our answer to this integral. So I'm now going to take this off because we've got this one written up here, factored. So, which residues are we interested in? Well, we are integrating over this region R, which is this circle. So we're interested in the residues that are either on or in the circle. So, sorry, the singularities. So the singularities are, so this will become 0 when z is 0. It all becomes 0 as well when z is 2. And also when z equals a half. So now let's put them up on this graph here. So z equals 0 will be here. Z equals 2 is here. And z equals a half is here. So z is 2, not in the circle, so it's not in our region R. So we're not interested in this one. So we didn't need this one. But 0 and a half we do need. So these are the two that we're interested in. So they're the good ones. So if we take the residues, 0 and a half. So the residues of f at 0, just cover this one up and plug in 0 for all the others using the cover up method. 0 squared is 0 plus 1. And then plug in 0 over here, got minus 2 times minus a half. And that will give us positive 1. And then we've got 1. So now let's look at our other residue at 1/2. So again, 1/2, that makes that disappear. So we plug in a half for all these. Half squared is a quarter plus 1, that's 5 over 4. And then we've got a half times a half minus 2. Half minus 2 is minus 3 over 2. So a half times minus 3 over 2. So that leaves us with 5 over 4. Half times minus 3 over 2 is minus 3 over 4. Okay, well, if we use the normal formula for complex fractions, we multiply top and bottom and divide by the multiplication of the middle two. So that will give us minus 20 over 12, which equals minus 5 over 3. Okay, let's write these residues down here. Okay, and now we can go on to the all-important formula now when we're integrating these functions. So I'll just rub this off now. So, okay, so what we do now is we multiply by 2 pi I the sum of the residues. So now what we can say is the integral from 0 to 2 pi cosine x 5 minus 4 cosine x dx equals, I'm just going to leave a gap here, and it's 2 pi I times the sum of the residues inside the circle. So it's 1 minus 5 over 3. So that's f at 0 plus the residue of f at 1/2, and not forgetting the I over 4. Because the integral here has taken this out as a constant multiple, so we then need to multiply the rest of this by that. Okay, so 2 and 4, that becomes the 2. I times I is I squared, which is minus 1, so that becomes minus 1/2. Residue of f at 0, that is 1. And a residue at 1/2 is minus 5 over 3. Okay. So 1 plus minus 5 over 3. So 1 minus 5 over 3 basically. So we've got 3 over 3 minus 5 over 3. So that becomes minus 2/3. That's what that is in there. So now minus 2/3 times 1/2. So that then becomes minus 2 on the top there, they cancel. 2 minuses cancel. So now we're just left with 1 over 3 and the pi. So let's just write the pi there as well, otherwise it's not making much sense. So then the answer is pi over 3. And that is the answer to this integral. Okay.